Hello everyone, I am Chandan Karfa. I am a faculty member in the Department of Computer Science and Engineering, IIT Guwahati. I am going to offer the course Formal Methods for System Verification through NPTEL platform. I want to thank NPTEL for giving me the opportunity to teach here, and also want to thank them for creating a beautiful learning platform for the students across the globe. Let's get into the course. So, if you seen this evolution of electronic computing starting from 1950s, it's touching everything, right? Starting from the personal computer, then internet, Wi-Fi, smart devices, then cloud, big data, GPUs, now this quantum systems, everything, right? It's impacting everything becoming smarter, it's impacting everywhere. We have creating so much of new business opportunity like e-commerce, online services, social connectivity, smart world, automation, everything, right? So, this everything become smart nowadays. Now, just pause for a second and think about what if in a flight which has lots of electronic systems and it does not malfunction for a second, right? You can think about the impact, right? Or in an automated car, a driverless car, and it does not detect some object in front of you running in fast. So, the impact can be catastrophic. So, on the other hand, it also can have a huge loss for the company. Just think about the Pentium bug in Intel. So, it was a bug. Intel tested the Pentium processor many times, right? And but some academic researcher identify flaw in their floating point division unit, and that's also very corner cases. Once in maybe some billion situation, there will be some bug in the decimal places, but that cost $500 million to Intel in 1990s, right? So, similarly, you think about the health devices like pacemaker or automated robot that do the operation or surgeries. So, if there are some problem, it can have a catastrophic effect. So, we have to ensure that whatever system we build is basically reliable, right? It is very important. But the question is that how do we do that? The answer is verification. So, when you develop a system, you have to make sure that it actually 100% correct. There is no bug inside it, and that process is called verification. Now, the question is how do you verify? The obvious way is simulation. It means you give input, check output, and check whether the output is correct. You already have the golden output. The other technique is formal verification, where we mathematically prove that your implementation is correct without any input. Okay. So, the difference between simulation based versus formal is that here for one test case you are checking. So, you effectively have some one test case. So, every iteration you can check for only one cases, right. But formal, maybe one property can cover a subset of the test cases. So, essentially without having input, with few property you can cover the entire search space, but for input, if there are too many input, you can probably do not cover all possible scenario. You think about there are 100 bit input and there are 2 to the power 100 possible values, you cannot simulate for everything, right. So, that is why formal verification is extremely important to make sure that your design is functionally correct. Now, how do you formally verify? So, there are three primary technique: theorem proving, model checking, and equivalence checking. So, in this course we will learn all these three techniques. So, I will give you a course planning. In the theorem proving part, we will learn the basic of logic, decision problem of logic, and the detail of the SAT solver, some basics of SMT solvers, and binary decision diagram. So, that is first part. And the second part is property checking, in which we will learn the basics of model checking, LTL model checking, CTL model checking, SAT based model checking, BDD based model checking, and bounded model checking. In the part 3, we will learn equivalence checking, primarily C2 RTL equivalence checking and verification of RTL optimizations using equivalence checking. And not but the least, at the end of the course, I will try to see how the large language model can assist the formal verification techniques. Okay. So, who can attend this course? Anybody, BTech, MTech students from computer science, electronics, electrical, interested in verification, it can be a very good course for them. Research scholar who is working on formal verification, this can be a good guiding course for them. Any verification engineer in the industry or the EDA tool developer, they can also refresh their knowledge on formal methods through this course. I just want to highlight one point here. So, there are two parts of this, right. So, somebody who will write property, right. So, they need to know what is LTL, what is CTL, how to write properties. So, I will provide case studies, I will give how to encode certain things into properties or theorem proving problem. So, this case studies help them to understand how to model that thing, that is for the verification engineer, On the other hand, some people has to develop this tool, right, this model checking tool or theorem proving tool, SAT solvers, right. So, they have to know what is the algorithm to check the satisfiability of a problem or how to check a property on an implementation, right. So, in this case they need to know this algorithm first. So, in this course we will cover both component, right. So, I hope this will be a very interesting course for everybody who is interested in formal verification, and I am happy to welcome everybody to my course. Thank you.